There is another moon around Saturn. It's a moon called Enceladus. This is an interesting moon in the context of life. What we see on Enceladus are fountains of ice rising up from the surface and disappearing off into space. Beautiful, but what we think is causing...
You can see that I try hard to emulate my idol. That said, I'm a mumbler. There's nothing I can do. I mumble, and I do have a lisp, a nasal voice. Is horrendous. So forgive me if I use my British accent when I present my work. Today we are going to talk about the twin paradox, which is the place where physics went wrong. That happened in 1905 or thereabouts, and wasn't Einstein's fault. The subject is obscure, and Einstein got messed up by his own Gedanken experiment. That said, I'm here to correct it, and so let's get it on.
Today we are going to be revisiting the twin paradox. The twin paradox was
a Gedanken experiment
that Albert Einstein proposed to support his special relativity theory. In 1905, Dr. Albert Einstein published his 3 papers. That year is celebrated as Annus Mirabilis. In 2005, I created the Hypergeometrical Universe Theory. That year, it was the centennial of Annus Mirabilis. It was a bad year to correct Albert Einstein. That said, great ideas don't come up according to a given schedule. They arrive when they arrive. The question that we will address here is if all inertial frames are equivalent. That's the principal postulate of special relativity and what is behind the twin paradox. Einstein lived in a 3D spatial manifold, one that he didn't believe to be embedded in a higher dimensionality space. Under those circumstances, Einstein proposed that the geometry of the space to be defined by the geometry of space-time and be controlled by the inner contents of the universe. In other words, space-time didn't have a global shape. Each and every mass distribution would locally deform the form space-time. I proposed a distinct geometry for the universe. In my theory, the Hypergeometrical Universe Theory, the universe looks like a sphere embedded in a 4-dimensional spatial manifold. It is more appropriately described as a hyperspherical hypersurface embedded in a 4D non-compact Euclidean spatial manifold. Here you can see that when we leave the hypersurface, we can clearly see its shape. Let's explore further the hyperspherical hypersurface. Here you can feel yourself at position A, look into the sky and seeing light from a galaxy at position B. Since Edwin Hubble's observations in 1929, we know that galaxies behave like dots on the surface of an expanding balloon. It is clear that this expanding balloon can be mapped to the light-speed expanding hyperspherical hypersurface. Notice that this simple model allows us to predict the positions of anything we see in the sky. For example, the galaxy on position B will travel only radially to position D in the outermost hyperspherical hypersurface, our current universe. In this figure I represented also the optical path of ancient photons. They are represented as a straight line. That said, this is a momentum mapping. The actual photon path is a curved line that is only determined by the moment of detection. The reason for that is the HU model's photons are waves on the top of much finer metric waves, called dilaton field, or metric waves. The wavelength of the dilaton field is the Compton wavelength of a hydrogen atom for gravitation and twice that value for charged particles, electrons, protons, antiprotons, and positrons. Being a 4D wave implies that energy is only extracted from the wave by dephasing events resulting in detection. Since all particles in the universe are surfing the inner dilation layer, the 4D shockwave, and that travels at the speed of light. Here you can see the optical path of ancient photons. They describe a curve in the 4D spatial manifold. The distance AC is equal to the difference in 4D radii. This optical path is the one that makes the rate of momentum loss by the photon constant with respect to absolute time, or the distance traversed along the radial direction, the distance traversed by the universe. Hermann Minkowski, a mathematician known for his work in developing the geometric interpretation of the theory of relativity, saw the Lorentz boost, a transformation used to describe how the observed properties of an object change when it moves at a constant velocity, as a kind of rotation in spacetime. Minkowski's insight was to treat time as a geometric dimension similar to the dimensions of space, allowing spacetime to be expressed as a four-dimensional manifold. He conceptualized the Lorentz boost as a rotation in this four-dimensional space, but with a crucial twist. The angle of this rotation was imaginary, which aligns with the mathematical properties of hyperbolic functions. Specifically, Minkowski used the idea that the hyperbolic tangent of this imaginary angle, denoted as alpha, is equal to the ratio of the velocity of the moving object v to the speed of light c, such that hyperbolic tangent of alpha is equal to v divided by light speed c. This relationship directly ties the velocity to a hyperbolic angle, reflecting the non-Euclidean geometry of spacetime under special relativity. This interpretation is particularly powerful because it unifies various effects of special relativity, like time dilation and length contraction, into a single coherent framework that describes them as geometric transformations of spacetime. Later, I will explain why the use of Euclidean or hyperbolic spaces or spacetime is arbitrary. In other words, a hyperbolic spacetime is not essential to the description of the universe. HU states that the non-traveling twin is at rest with respect to the fabric of space, green circle. This is supported by Dr. Edwin Hubble's observations. He discovered that galaxies were like dots on a balloon. The idiosyncratic absolute velocity of the Milky Way is 600 km per second, or 0.2% of the speed of light. This idiosyncratic speed is due to librations around a center of mass. Here we show the two cross-sections of the LEHU. The right panel contains only space. There you can see a circle representing the universe along the single coordinate, single direction and the radial direction, perpendicular to our 3D universe. The left panel contains spacetime. There you can see phi, absolute time multiplied by the speed of light, and tau, proper time multiplied by the speed of light. We can also see the angle between the normal to the 3D volume of the particle and the radial direction. Minkowski explained that Lorentz boosts were equivalent to projections of a reference frame onto another. He didn't push, as far as I know, the idea that the reference frame was an absolute reference frame. The reason is simple. Minkowski spacetime is just the linearization, small distance approximation, where the universe is just a hyperplane moving along time at the speed of light. You might say, moving along time as any speed is nonsense. And you would be right. Minkowski spacetime only makes any sense with the addition of something traveling at the speed of light. Who proposed that something is the light speed expanding hyperspherical hypersurface, which expands within a 4D spatial manifold. The inset on the right panel, spacetime cross-section, shows that for short distances, the circles become hyperplanes and you recover Minkowski spacetime. It is clear that geometry dt, differential of absolute time, divided by d tau, differential of proper time, is equal to hyperbolic cosine of alpha. From that one can find the value for delta tau. To make the integral simpler, I considered a constant acceleration, so v is equal to a times t and hyperbolic tangent of alpha is equal to a times t divided by century. It is clear that one can minimize the importance of the accelerated sections by having a fast acceleration. Here we see the final value of the time interval for the first accelerated section, tau 0. Again, high acceleration minimized the influence of the accelerated sections on the final aging. Here you can see the Type 1a supernova data obtained by Dr. Adam Rees and his group. HU explains this data with its epoch-dependent G. As you can see, the data is perfectly fitted with just two parameters, the current 4D radius of the universe and an exponent factor of the g dependence of the absolute luminosity of the supernova. In other words, HU lifts the supernova as standard candles postulate and make the type 1a supernova g dependent. Compare this 2-parameter model with the 7-parameter model called FLRW or Standard Model of Cosmology. HU model uses only 2 parameters and doesn't require any dark matter or dark energy. It also doesn't require space to be stretched or display distances that are not consistent with the expected age of the universe. Only in HU, the Hubble constant is equal to the inverse of the age of the universe. In HU it is equal to c divided by the 4D radius of the universe. HU fitting yielded 14.04 billion light-years for the 4D radius of the universe and 69.69 kilometers per megaparsec second. The whole twin trip comprises of ramping up velocity coasting outwards, reversing velocity coasting back, slowing down velocity to full stop, 4 accelerated sections of no importance and 2 coasting sections at full speed, versus if these 2 inertial sections are equivalent to the earthly twin reference frame, the aging should be the same. The standard explanation that acceleration makes the traveling twin age is nonsensical according to Minkowski. Even in general relativity, time dilation is associated with only velocity. The gravitational time dilation is explained using energy conservation for a body falling from an infinite distance. At infinity, both kinetic and gravitational potential energies are null, so the total energy is zero. Their sum should remain zero at any position. That creates a relationship between velocity and distance from the gravitational source. That is the relationship that yields the equation for gravitational time dilation. The time delay associated with the accelerated sections of the twin trip can be minimized, leaving only the time dilation from the coasting sections. If inertial frames were equivalent, the aging process on both twins would be the same. Since they are not, we know that time dilation is real from the dilation of subatomic particle lifetimes. The basic principle of relativity is wrong. Inertial frames are not equivalent. How could we get it wrong for 100 years? Group thinking, the lack of a replacement model, censoring of disagreeing ideas, mine. Not realizing why all galaxies are like dots on a balloon, their idiosyncratic absolute velocities is close to zero. Galaxies are formed after gases travel enough of a distance to reduce their idiosyncratic velocities. In other words, atoms traveled hundreds of millions of years. Consider a hydrogen atom traveling in 4D along alpha 1. After some time, the angle alpha 1 becomes alpha 2, where alpha 2 is always smaller than alpha 1. This means that the idiosyncratic velocity diminishes as the gases traveled. Conversely, the reason for motion is to relax the fabric of space. HU provides the reason for motion in this universe. What did we learn? The twin paradox was never lifted and it doomed relativity. Its resolution requires the existence of an absolute reference frame in Minkowski spacetime. The hypergeometrical universe proposes exactly that absolute reference and renounces covariance and the equivalence of all inertial frames. Whose laws of nature are derived from first principles on a 4D spatial manifold. So, inertial reference frames are not equivalent. The only reason the traveling twin aged slower is because the staying twin was at rest with respect to the fabric of space. How could we get it wrong for 100 years? Einstein should have known the postulate that all inertial reference frames are equivalent to be wrong, since Hubble's observation that galaxies were receding at a velocity that was correlated to distance. In other words, that dots on a balloon analogy for galaxies spells the existence of a preferred referential frame where galaxies are at rest. Einstein didn't acknowledge that fact. That would be the same as renouncing relativity. That all inertial frames are equivalent or covariance of laws is the central theme of relativity. Summary: the velocity that goes into Lorentz transformations and Minkowski spacetime is the absolute velocity. That is how one lifts the twin paradox. What is next? Thank you for watching my video. Next, I will explain, where did Einstein go wrong with time dilation? What is time? What are the hypergeometrical universe theory hypotheses? What is the fundamental dilator and the quantum Lagrangian principle? What is this universe's frequency? How to derive the laws of nature from first principles? Provide the new standard model for particle physics. What is next? Explain the spiral galaxy rotation curve conundrum. Explain the early galaxy formation conundrum. Explain the coma cluster, dark matter, conundrum. Explain the bullet cluster observation. Explain what to do to be able to travel at relativistic speeds. How the universe was created and how will it end. How to solve your energy problems and reach out to the stars. How did I create the map of the observable and unobservable universe? What is Earth location in the universe map, etc.
So, what is the take-home lesson? The take-home lesson is that since 1929, since Hubble observations, we know that galaxies are like dots on an expanding balloon. And that means that galaxies are sitting still at a reference frame. And in our reference frame, that is the hyperspherical light-speed expanding hypersurface. This means that there is a lab frame which is sitting still, has absolute zero velocity or close to it. In the case of the Milky Way, is 0.2% of c, and any relativistic object or particle will have also an absolute relativistic velocity. In other sense, there is a conflation between absolute relativistic velocity and relative relativistic velocity, because our relative reference frame is sitting still, is at rest. So that's how you solve between paradox. Thank you very much.